Cho, and it's my great honor and pleasure to introduce Chad Jenkins, who is an associate professor at University of Michigan. So Chad and I, we go way back at least 10 years. I met him at ICDL conference for the first time. I was greatly impressed by his robotics work. So he's an accomplished, outstanding roboticist working on a really important mission to make an impact on human life. Right? So we'll tell you a lot about that. So he got his bachelor degree at Alma College in Michigan, and then he got his MS degree at Georgia Tech and PhD at USC and the Maya Metallic. Right? And then he was for a long time a professor at the Brown University. And then he's back to his hometown, I guess, in Michigan. He has a very distinguished career. So he got the Sloan Fellowship and PK's, NSF, and the Presidential Early Career Award, which is a very prestigious award given by the President of the United States. It's wow, exactly. And then he has a really, I really don't like this kind of very, very dry introduction. So what I usually do is go to his web page. And he has really cool stuff on his web page. His URL is ocj.org. It's not C character and J character. It's C as in C, and then J as in J, blue J. It's really cool. And he's done this video sequence for National Geographic TV channel. He also gave a TED talk and so on. So I'm expecting him to actually top his performance that he gave at the previous TED presentation. So please welcome Chad.
All right, I'm going to try the stage for a little bit, see how that works. Hopefully my laptop stays powered. Thank you very much for memorizing all of that stuff on my webpage. That was really cool. And I'll try to keep it entertaining because it is 8 o'clock in the morning after the banquet. So I'm Chad Jenkins. I'm the leader of the Laboratory for Progress at the University of Michigan. That's Perception, Robotics, and Grounded Reasoning Systems. And the title of my talk is Perception, People and Scenes for Robot Learning from Demonstration. But really what I'm really trying to do, more than anything else, is think about how we can make the world programmable through robots. How can we take all the things that are in our world, say, move that chair over there, can you make me a meal, can you put this table together for me? And have robots be able to do that in a way that's going to be seamless and accessible to people. And that's really what we're trying to do. But before I do that, I want to make it engaging and interactive. And so I've been faculty for about 13 years, and I want to ask you, what do you think is the question that I often get the most when I'm walking around campus or anything like that? Any guesses on what people tend to ask me first?
Are you building Skynet?
Am I building Skynet? No, because if they have to talk to me first to know I'm a roboticist. Typically what I get is, but I appreciate the guess, by the way. Typically I get is, are you with the football team? And I say no, no. And have you seen how big those guys are? Like I'm a decent sized guy. Those guys are really big. And so just as a point, I played. My distraction in graduate school is I played rugby, because when you're playing rugby, you can't really be thinking about what are my papers doing or why didn't this result work. That was my escape. And decent sized guy, but those guys are a lot bigger. So just a word to graduate students: get something that'll take your mind off your work while you're in research. Any question about anything? What do you think the next question is? I'm usually asked. Anybody? Just guess. Somebody just yell out something. What's that?
Do you have one at home?
Do I have what?
Do you have a robot at home?
Do I have a robot at home? I don't. I do get that question, but usually what comes first before that is, when will I graduate? And I say no. I say I'm actually faculty in computer science. I graduated several years ago, and And so and that usually follows up with, can you fix my blank? Can you fix my, usually it starts off with printer, but then it oftentimes goes into website, iPad, all sorts of stuff. And I say, University of Michigan costs a lot and they pay me a lot of money. So I can probably do it, but it'll cost you a lot of money. And so I say, what I actually do is I program autonomous robots. And usually and I talk about the kind of robots we have. So this is the PR2 that we had at Brown University. 2 arms, can move around, it's got plenty of sensors, and people are fascinated by that. But it usually goes, will they take over the world like Skynet, right? And I say, robots aren't nearly that smart. There's still a long way to go, but maybe the people here have some thoughts on how to make them much smarter. And I think robots will be helping humanity. So as you said, what we have is, what I've done before is I really care about what the impact of our technology is going to be. And so we did a TED Talk with Henry Evans, so this is a TED Talk from a few years back. And Henry suffered a stroke several years ago, and it rendered him the inability to move and speak. And so he relies on people to do every sort of activity of daily living. And this is one thing where I think robots can make a big difference, because what Henry was able to do, using some of the technologies that we've developed in my lab, some of our colleagues at Georgia Tech and various other people, is allow Henry to be able to use technologies that are available to him, like the web, like standard personal computers, and be able to control robots to start the beginnings of being able to do things on his own, to live independently, to be able to scratch an itch. Think about it, if you couldn't scratch, every time you had an itch, you couldn't scratch it, right? Henry's able to do that. Being able to shave yourself, be able to feed yourself. Those are basic things where I think robots can make a big difference in terms of helping, for enabling independent living for not just people who are physically disabled, but also as we get older, we have a growing aging population where this could be a big benefit. In fact, Charlie Kim, who's the guy in the corner right there, said that was the first time Henry was able to shave himself in 10 years. And that's really powerful. One of the most inspiring things I've had in my experiences I've had in my career. And at that point, usually people say that sounds cool or awesome, or that doesn't sound like a real job. And I say, and we start talking about robots and things like that. But usually it comes down to the question that's the big question in the end. So where's my robot? When are we going to get this technology? They've been seeing it. They have a little vacuum cleaner, but it only does a halfway decent job on your floor. We have autonomous cars, but that's still a little bit ways off. I'm really thinking about mobile manipulation platforms. And when are these robots going to be available for you to use to do? People talk about Rosie the robot, sort of like Rosie the robot, like these types of platforms that we have right now. Rosie is not what comes to mind, but if you want to think about that, when are you going to get a platform like that? And so what we have is the PR2, which I described before on the right, and on the left is the Fetch Robotics Mobile Manipulator. And so I bought the Fetch Robotics system when I came to Michigan. And so these platforms can move around. They're autonomous. They can do all sorts of things and they can pick up stuff. They're very physically capable. Another question: how much do you think these robots cost? Was that too much? Like that $500,000? That's a good guess. Any other guesses? I'm sure we didn't have that much alcohol last night. I need one more guess to have confidence.
1 million.
1 million. All right. Actually, if I plot these by I forgot to say one more thing. So we want these systems. These systems will be capable of doing activities of daily living, being able to work in natural and structured human environments, and be able to do things like cooking. And with that, these platforms are essentially going to decrease in cost. So if we plot how much they cost by the year that I bought them, so the PR2 cost me about $400,000, more than my house. And I bought that in 2009. I bought the Fetch mobile manipulator in 2015 for $100,000, right? If we compare that to the first robot that I really started working with, which was the NASA Robonaut, and I started working with in 2002. That robot, I don't actually have an actual number, but 1.5 million is the number that I've oftentimes heard. And so if you remember linear algebra and how we fit your favorite nth order polynomial, if we do that and we extend that out, we look at the trend, I would make the argument that the kind of robots that you're going to be able to use in your research, potentially in nursing homes or other types of areas, other types of places, it's going to be about $40,000. That's something you can write into your grant for about 2020, right? And so, that cost is going to go down. It's going to go down from like the cost of, let's say, a luxury car down to maybe an economy car. And maybe, by the time your children my children are doing research, it could be about $15,000 a robot. And that's what we're looking at, right? And it'll be like your commodity computer. You don't think about making your computer, you just buy it and you use it and you go. That's what we're looking at. So, when we're thinking about the span of how autonomous robotics, the story of robotics, not just the platform, but how autonomous robotics forms after that, there's some major stages that we can talk about. One is really up through the time I was in graduate school. Really, we were thinking about robots as remote control devices, right? Remote control is just sort of like, some human operator is going to be physical, or is going to have some motion capture device on them, or some sort of joystick, and they're going to be just moving the robot around. The robot has really no intelligence. You're just switching out the human's embodiment for the robot's embodiment. With the rise of sensors that have come out, it's really been able to have robots be able to put that there. So robots can move around and do things like move things from point A to point B. If you think about autonomous car, it's really picking you at point A and then taking you to over there to some point B. For our robotic systems, it's very similar. You just want to grab something and go put it somewhere else. And what we're really trying to move towards, and this is sort of the next level for these types of robots that are coming up, is that we want to be able to start to delegate tasks to robots. We want to say, do this task for me, right? Not just put this thing over there, but making a meal, where there may be many steps where you have to put various things in various places in a particular order. And so this is where we're really coming towards. That's once you're able to delegate tasks to robots, then you're going to be able to phrase programs on top of that, and that's what's going to allow you to be able to program your world. So let's start from the beginning. So let's talk about remote control devices let's think about robots as remote control or teleoperation devices. So one thing that I should note is that the Robonaut is now, there's actually a Robonaut 2 on the International Space Station that is orbiting around us. And so these robots are meant to do things that take tasks that the robots would have to do, the housekeeping tasks, such as wiping down rails or doing maintenance tasks, and take that off the astronaut stack so they can be able to do the science that they actually went up to the station to do. And so in order to do that, right now it still is treated like a remote control task where there's somebody on the ground or that has like a big motion capture system. They have to sit in this very uncomfortable position to be able to move the robot around. They have this head-mounted display there where they can see what the robot sees. And it's really, that really is a cumbersome task. I can only do that for maybe 10 minutes before I'm motion sick. Certain people can do it for an hour, but you can't do it for very long. And so one thing we tried to do to relax this constraint is start to develop, and while I was sort of doing a postdoc, is be able to have untethered motion capture devices. So if you think about a Wiimote or an IMU-based device, we put that on the different parts of the body, and then the person can actually move around and get up and do things instead of being restricted to the chair. And so this is the kind of motion capture system. This is just sort of an example of what teleoperation would look like. So you have the Robonaut moving around. My colleague Nathan Miller is essentially moving his arms, and the robot can copy his motions. And so what this is really doing is just straight remote control. Nathan can move in any pose. We can track his pose. That pose gets copied to the robot. And this is great, but what it lacks is the ability to adapt to different types of environments or understand anything about Nathan's intentions. And so what we were thinking about early on during this phase is, how do we generalize human motion into adaptable robot autonomy? And at the time, we thought the right answer would be imitation learning. So how could we have a person do something, demonstrate something, and then the robot would understand it enough that it could build an intermediate representation that it could generalize to different types of scenes? And at this time, we were thinking about imitation learning and sort of, we were taking a mirror neuron-inspired approach. So at the time, there was a lot of rage about mirror neurons. Do people know what mirror neurons are? I'm not sure. Maybe half. So the idea of a mirror neuron is that they're areas of the brain that fire whenever you whenever you see, think about, or perform a particular type of motion or a particular type of action. And so these types of motions, these types of areas essentially will fire whenever you see somebody else doing something, and that allows you to sort of copy that motion or get an intermediate representation of what they're doing. These mirror neurons were hypothesized to be linked to spinal fields, which are sort of convergent potentials that sit inside your central nervous system that essentially encode the motion dynamics of acting as sort of low-level motion primitives. And we tried to uncover these primitives through a process of motion segmentation. So we would just have motions of people doing their normal activities of daily living. We would take that motion capture data, segment it, cluster it into primitives, and that would give us these dynamical systems that we could then use to both predict human motion for recognizing gestures, or even and then also be able to simultaneously perform control of those same gestures on our robot. We had a number of different publications on this, but so those are there. So you're welcome to look at my Google Scholar and see what we've done. But what it led us to was an interesting idea, that what we really didn't want was just motion capture. We wanted controller capture. And so controller capture became this idea that what we'd have is a person would demonstrate something to us in a video. So let's say we had a monocular video of a person jumping. And what we wanted to get out of that was a finite state machine that could reproduce that same motion, but also adapt to new environments. So we'd see that video, we'd get a controller. That controller would then be able to reconstruct the original motion that we saw, but then we would also be able to adapt that motion to new environments. So if we change the slope, the robot should be able to adapt to that slope. If we change the frictional properties of the ground, the robot should be able to adapt to those changes as well. And so this was really what we did. And so this work was from 2012. So the ability to estimate controllers from demonstration was really cool. Most of this work in terms of estimated finite state machine, in addition to doing motion segmentation, we were going to minimize an objective function that took into account how well our controller acted, how well our controller performed with respect to what we saw in the original demonstrated image. There's also priors on the potential poses where the body, you couldn't exceed joint or torque limits. There was priors on contacts that we had, and then you also had to remain stable. And so really the likelihood was the big part of this. So what you're going to see is an overlay of the silhouette that we extract from the image and how our controller performs with the rigid body physics simulation. And so when we're getting things right, we have low energy and they both match. But when we don't match, then we get high energy and it falls over, and that's bad. And so this kind of objective function essentially allows us to estimate these finite state machines. And we can use these in a variety of scenarios. So this is from somebody else's, from a related paper. We took their original mocap, the original monocular video, and we were able to estimate the motion that they were able to perform, as well as be able to adapt it to a trampoline type surface. And so what we're getting is not just the motion, but we're getting a controller that allows us to adapt to this new circumstance. Similarly, if we have a back handspring, so we had a gymnast come in, and my student Merrick Vondrek had a gymnast come in, and she basically did a back handspring, and we could reproduce that motion. And then we could think of new scenarios where we could then just apply that motion and still get the same type of control where the system can adapt. And so this was one of the results that we got. In addition, you don't know what you can do until you know what you can't do, and so failure cases are really important. So if we take the same controller and we apply it to just a slope, it should not work, and it didn't. And so that was a good sign. We should not have superhuman abilities as well. So if we have the system just sort of, it should not be able to fly in the air. And so these failure cases are really important for showing us for giving us grounding for what we want to do. And so you should be asking yourself, I was pitched as a roboticist, why am I just seeing simulations? Well, at that time, we really didn't have a lot of simulations. I mean, we didn't really have a lot of robots that we could use. The robot that was available, $1.5 million, they do not want that robot necessarily doing all sorts of crazy things. And so what happened over time is that robots got better. We needed better robots, we needed better sensors. And this takes us to the next part of the story, where what happened is that the cost of robots started to go down. More importantly, the cost of sensors went down. And that takes us to really where robot autonomy started to play a real role. And this is really what we call pick and place. Pick something up and go place it somewhere else. And so this gets to autonomous robotics. Autonomous robotics, if you haven't heard it, is really characterized by 3 words. Sense, plan, and act. That means that your robot has to be able to perceive a model of the world. And with that model of the world, it has to be able to plan and search over a potential set of actions and execute actions that will get you from your current state to the goal. And we don't really care how this happens. It could happen from a number of different ways, but this is roughly the process that we have right now. We do have great planners. We do have great action systems. I wouldn't say that any of them are optimal. In fact, I think these are areas where potentially deep learning and neural networks could overtake search-based methods. But our real problem is sensing, and that's where neural networks have been a big boon in recent years. And our group is trying to think about how we synthesize that with probabilistic generative reasoning. But what's really driven, more so than the computation, or just as much as the computation, I should say, what's really driven is our change in sensors. So with our robot that we have 2 sensors that really define what the current state of the art in autonomous robotics. One of them is the Kinect. Anybody play Xbox? No Xbox here, okay. 2 Xbox. Can I get a third? A third Xbox, thank you. But so essentially, Microsoft bought a company that develops 3D RGBD sensors, which has been great for video games, but even more awesome for robotics, and I'll show a little bit from that later. Your laser rangefinder. The laser rangefinder is essentially what has allowed navigation and mapping to work. So if you take a look at what the laser rangefinder does, so if we look on the screen here, the laser rangefinder is embedded in the base of the robot. And if we think of that purple dot, I know it's hard to see, but that dot right there, what you can get around the dot, which is the robot's current location, is